So good morning. It's not a good strategic slot to keep your attention alive, but well. My name is Patrick Van Reeth. I belong to Hewlett-Packard. I'm in charge of developing the GPU computing activity within the HPC Competency Center. I'm here to back up my colleague Frank Bethke, which was normally here to do some presentation about HPC stuff at HP. But well, have the pleasure to be here. I will make a presentation about an economic analysis about the way it makes or it makes no sense to migrate an application from a pure traditional CPU environment to a hybrid CPU plus GPU environment. So as an introduction, today, the HPC users are faced to a kind of contradiction, which comes from the fact that HPC users are expecting more and more flops and are addressing bigger and bigger data sets. And faced to that, there is another constraint, which is more and more, let's say, aggressive, which comes from the fact that we are willing to reduce the power costs, the cooling costs, to reduce the density as well, and all this with the while keeping in mind the way that we want to keep a good price-performance ratio. And faced to that, GPUs can bring, let's say, a kind of supplement of silicon, which brings to the CPU some supplement multi-core, which are definitely devoted to computation. So I won't go into details about how the GPUs are structured, but well, the goal of my presentation here is to do first a very short technical approach about the migration, and then about the economic approach of it. So let's start from an existing application, which has been written some years ago, based on CPU, sometimes on CPU with one core, one CPU in one server. And the idea here is to see if it can make sense to migrate to GPU. So the first step, we are used to meet customers which are willing to move their application to GPU, and we are trying to help them to do this transition. And the first thing that we recommend to do is to understand how the existing code is structured. And for example, we are tracking what are the areas which are the most computationally expensive, for example, all the inner loops. We are probing also the balancing which is done between the different servers when we are talking about MPI code, between the different cores within a server and between, the CPUs within the same servers. We are also examining how the data sets are split within the server and within the cluster, and we are probing the communications. And faced to that, today there is a toolbox which is richer and richer every day, and the toolbox is made of multi-core CPUs. We have more and more cores, CPUs. We have some memory whose bandwidths and latencies is improving year after year. We have some fast interconnects like InfiniBand, for example. And we have now the GPU building blocks. And we have all the software environments which makes all those ingredients able to run efficiently in a HPC environment. So these are the different points that we are taking into account when we are looking to an existing application. But what we always say to customers is that we have to be agnostic first. What I mean here is that when we are talking about an application which has been written for an old-style workstation with one CPU, one core, and if we do directly a porting to a GPU environment, we will observe some fantastic speed-up, which can be up to hundreds of speed-up factor. But sometimes, and this is what we like to do, we are also exploring the CPU dimension with all the cores which are available today, and sometimes CPUs are really, really efficient if we optimize the code as it was written before, and if we optimize it on a multi-core environment. So this is the first advice that we give. We have to stay agnostic first. Then, once this analysis has been done, we are looking to the different minds that can be the success factors of GPUs. And for example, when we are looking to the existing code and we want to say how viable it can be on a GPU environment, we have to think about how to redesign the code architecture in order to scale it at the right levels, at the node level, at the CPU level, at the core level, and at the GPU level. And what we have to think about is that with GPU, embarrassingly parallel is good. We have to optimize the calculation versus the memory access. And when we necessarily have to access to the memory, we have to use the cache when possible instead of the CPU memory, for example, because this becomes a disaster when we have a communication between a GPU and the CPU memory in terms of time. We have to map the threads on the cores very importantly. And we have to, as I said, to minimize the CPU to GPU transfers. One very important point, if we are considering the way that the data were partitioned in a CPU environment, this must not be a guidance to split or to partition the data set on a GPU environment. And it can be completely differently split if we want to stay within the GPU memory on board. Okay. And one very important point, let's say the beauty of a porting comes from the fact that we can obtain a very good balancing between the code executed on the CPU side while it's executed on the GPU side. And a very well-balanced code has exactly or more or less the same execution time on both. And for this reason, when we have explored all the different parts that I've mentioned on the slide before, we have now to determine the right platform. And what I want to say here is that putting a GPU within a system is not exactly like playing Lego. What I mean here is that there are some platforms which can be really appropriate to some application and not for some others. And what I just said about the split between the execution time on the CPU and on the GPU, this will determine, for example, the number of GPUs that will be associated to a certain number of CPUs. Some applications are really running well with one CPU core associated to one GPU, and some others are really working well with 2 or 4 CPUs associated with one GPU. So all the technical approach that I was mentioning before will guide us to the kind of hardware platform we will define for a certain application. We have also to consider the fact that the communication today between the GPU and the CPU is done via the PCI Express link. And depending on the communication density between the CPUs and the GPU, it will make sense or not to have several GPUs sharing the same PCI Express. If this density is not that big, then it will be possible to have, for example, this kind of external systems provided by NVIDIA with 4 GPUs that can be connected to the server via the same PCI Express. It can make sense. But for some other application, we absolutely need to dedicate one GPU to the CPUs via one dedicated PCI Express 16x slots, for example. The way that the application takes advantage of single or double precision will determine the GPU type. And the dataset size can also be important in order to determine what kind of node we can have. And the price, for sure, is important. So faced to all these constraints, HP has a wide portfolio, which is made of very different form factors, standard ProLiant servers, which are rackable, or the scalable lines, which can host up to 8 GPUs in one server, or we can also have blade form factor, which can host some GPUs. So I won't go into details for all these servers, but the important thing is that depending on your application environment, it can make sense to dedicate a type of servers with a certain number of GPUs. Okay, so I will now spend the last 10 minutes to talk about the economic approach on 2 different applications that were, let's say, some homegrown applications belonging to customers, which have been ported to hybrid environment. And this study has been done using HP machines, and it has been done in collaboration with our colleagues from CAPS Entreprise. So CAPS is a French company which provides either some tools for doing some migrations and some services in order to, let's say, help customers to migrate their existing application from a historical old environment to another one, which can be either optimized in terms of CPUs or in terms of GPUs. And they have especially a workbench whose name is HMPP, which greatly helps for that. So we have done this work together with CAPS. And what we have considered is either the capital expenses and the operational expenses. In terms of capital expenses, we have considered the system acquisition costs, which includes the server, the GPUs, the interconnect. And we have considered that these systems have been, will be amortized over a 3-year period. A very important point, I have talked here about homegrown applications. In many cases, we are not talking about homegrown applications, and we are talking about commercial applications whose licensing model greatly influences the final price. So in this case, I'm not talking about commercial applications, I'm talking about free licenses, if I can say. We have taken into consideration the migration cost as well, expressed in man-month, and we have considered that the migration effort is going beyond the 3 years that the hardware is attached to. Here we are talking about 10 years for the migration effort. Especially with the kind of tools provided by CAPS, we are able to take advantage of these tools for a longer period than 3 years for sure. In terms of operational expenses, we have taken into consideration the energy costs, which consists in system power consumption plus the cooling. And we have taken into account the maintenance costs with the system maintenance and the support. The conditions of the test, we have a small cluster made of 4 nodes, which are 4 SL390 from the scalable line of HP. These nodes are able to host 0 or 1 or 2 or 3 GPUs. And the analysis for the application that I will present afterwards has been done with all these different combinations. So the GPUs were C2050 from the Fermi family. We have used this server, the SL390, which is a 2 sockets, 2 CPU. We have used for the test that we done the X5670 Westmere 6-core processors, and we have up to 48 gigabytes memory. In terms of energy power, we have used an ampere meter in order to measure the power consumption of the server, and we have considered an electricity rate of 7 euro cents per kilowatt hour, which is an average rate in France. It can be dramatically different in some other countries. We have also considered that the cooling cost represents 50% of the server consumption. This can change a lot depending on the cooling type that we can observe on different data centers. And just for information, we have neglected the power consumption of the interconnect because we were not able to measure it the same way that we were measuring the system. But most of time, the power consumption of the switches is neglected. One important thing that I forgot to say is that those servers have InfiniBand on board. Okay, so those are the two applications that we have taken into consideration. The one that we call the application 1 is a Monte Carlo simulation, which is done for thermal radiation. It's an MPI code. It's a very scalable code, that we tested over 4 nodes only, but due to its structure, we can predict that it can be very scalable with a high number of nodes. The migration cost was 1 man-month. Done once again with the tool from CAPS, the tool HMPP. The second application is an astrophysics application, which is also an MPI code. We know that it requires 3 GPUs per node because, let's say, the way the data sets are split in subdomains makes that 3 GPUs have to be connected in order to address these sub-data sets. And for this application, the migration costs are 2 man-month. Okay, so this represents the power consumption depending on the execution time. The dark blue curve represents the system without any GPU. The green one represents the system with the same system but with 3 GPUs. So you can see that there is a very big speed up factor. And the yellow one represents 2 GPUs and the orange one represents 3 GPUs. So for this application, clearly we can see that there is an interesting speed-up factor in terms of functionalities. The second application shows a very different behavior. Please don't consider the orange one, which should be too long to explain. Just consider the green one and the blue one. The blue one is a cluster made of 4 nodes without any GPU. And the green one represents the same cluster but with 3 GPUs. So here you can see that the execution time is not dramatically lower than the execution time without any GPU. And here, when looking at this curve, which is very hectic and which presents some spikes, we can understand the reason why it cannot be accelerated. And this comes from the fact that there are a lot of communication in this application. That means that there are a lot of connection between the GPUs and the CPU memory and a lot of connection between the different nodes. And this can be observed because during these communications, the GPU activity is lower and the power consumption is lower. This is a very big table. This is the last but 2 slide. This is a big table that represents, in fact, for the application 1 and for the application 2, the different costs in terms of system costs, maintenance costs, energy costs, and the sum of all of that, and the execution time here. Regarding the first application, I have calculated the cost per run. And we have, with a traditional cluster made of 4 nodes, only CPUs only, no GPUs, we have a global cost which is a little bit less than 2.5 euros. And with 1 GPU, we are at 1 euro. With 2 GPUs, we are at, let's say, 0.7 euros and let's say 0.6 euros with 3 GPUs. So the light blue represent the system costs, the dark blue represent the maintenance cost, the green represent the energy cost. One slight remark, here I'm talking about list price without any discount. So the light blue can be somehow flexible, I would say. The red part on the top of each one of these 3 bars are representing the migration costs spread over 4 nodes only. As I said before, this application is very scalable, which means that if we have not 4 nodes but 8 nodes, this red part has to be reduced by a factor of 2, etc. So this clearly means that the migration cost can be neglected if we are considering big machines. For the second application, so it clearly means if we look at the 2 first bars, the first one has no GPUs, the second one has 3 GPUs. So there is a big price difference, which means that clearly in this case the GPUs does not make sense. But there is a very interesting thing between the bar 2 and the bar 3, which comes from the fact that in this application, the CPU activity is really not important. And due to this, there is a thing that we have to consider, which comes from the fact that in this particular case, we can buy a server which has a very low CPU price. We can consider only 2 or 4 cores, and we can consider very low frequencies. It can sensibly reduce the cost without any big impact on the performance. Another comment, today with existing technology we have, and it's not interesting to work with these GPUs, but the future of the technology, either from the GPUs or from the GPU direct consideration, it could reduce rapidly this bar. So we have to stay tuned with the evolution of the technology. My conclusions here, as I said before, when you have to consider a migration from a CPU environment to a hybrid environment, we have to be agnostic first. And we have to know that GPUs can do miracles, but CPUs with the cores that we have today are able to do so as well. Second, learning. The architecture of the system is very important. Depending on the type of application, we have to consider several possibilities in terms of architecture based on the number of CPUs in one server, the number of GPU, the connection between the CPU and GPU, and the interconnect as well. The goal of my presentation was also to convince you that we have to take into consideration the total cost of ownership, I mean the capital expenses and the operational expenses when you are willing to move to GPU. For the application 1, it was really easy to see that the GPU extra cost can be easily amortized. And regarding the second application, even if the price performance is not compensated by the short speed up that we have, it can be improved for the next generation of GPUs. Once again, here I have not taken into account the licensing policy, which can dramatically change this economical approach. And then the last point, on large machine, the migration costs, and especially when we are using some efficient tools like the HMPP tools that I was talking about, we can consider that the migration costs are really neglectable. And that's all.